Is technological progress actually progress? What if instead of a staircase, technological history is a loop? We are told civilization evolved gradually. Stone, bronze, iron, machines, industry, AI. But engineering itself contains a recursion problem. How do you create the first tool without tools? And this is not a childish question. It's structurally identical to what came first, the chicken or the egg. Today, I'm going to explore how the official historical narrative stumbles over what appears to be a trivial technological detail. Modern engineering logic works like this. We use more complex tools to make simpler ones, not the other way around, except maybe for 3D printing. So why is this rule violated in history? Academia calls this the bootstrapping problem and explains it with gradual iteration, primitive fabrication, incremental refinement. But there is no full experimental reconstruction of that process. Only fragments, only inference. And inference is a polite word for conjecture. We will call this the first tool paradox. Part 1. Bronze and Iron Age due diligence. Number 1. The setup. The missing ingredient. We accept the Bronze Age as fact. Mesopotamia, ancient Egypt, cradle of civilization. But bronze is not mined. It is engineered, which means the Bronze Age was never just about metal. It was about supply chains. Copper plus tin. An alloy. Geology points to the absence of tin deposits in the cradle of civilization areas. Tin is rare. To sustain bronze production, estimates suggest 100 to 200 tons of tin annually. Now the question, how do you move that much material from the British Isles and Central Asia to Babylon? Without compasses, without steel tools, without modern navigation. How much time would it take? Number 2. The Logistical Heresy. One donkey carries around 70 kilograms. 100 tons equal approximately 1,400 donkey loads. That's only land transport. At sea, we cite the Uluburun shipwreck. But no full replication exists of such long-range routes using only Bronze Age tech. Yet, the system is assumed to be stable for centuries. This is presented as normal history. But structurally, it resembles a supply chain miracle. And that is before theft, weather delays, war, spoilage, and route failure. Number 3. The Iron Age shift. Now, the contradiction gets worse. Iron is everywhere. Problem solved? Not quite. Early iron is bloom iron, porous, impure, labor-intensive. Roman steel is case-hardened through carburization at the surface over a soft iron core. Functional? Yes. Precise? Questionable. Roman needles? Often bronze. So, how do you produce precision chisels for high-detail marble sculptures and masonry we observe in museums around the world, with that brittle metalwork? Academics would point to a 2023 study of an iron chisel from Rocha do Vigio in Portugal, dated back to around 900 BCE, as evidence that Iberian stonemasons may already have had access to steel tools capable of working very hard stone. But just like with Uluburun shipwreck case, a critical mind should question, does a single archaeological find support the entire historical narrative of an era? It could be a misinterpretation, it could be an anomaly, in extreme cases, even a forgery. Number 4. Radiocarbon dating flaws. Now add the known limitations of radiocarbon dating. The process relies on assumptions that can introduce bias. For example, it assumes the sample is perfectly preserved and representative. Yet, factors like contamination, environmental exposure, or the old wood problem, dating material that predates its actual human use, can significantly skew results. And suddenly, the narrative doesn't seem so neat at all. If ancient metallurgy looks shaky, precision mechanics are even less forgiving. Part 2. Renaissance precision problem. Now move forward. Renaissance artifacts. Mechanical clocks, automatons, armillary spheres. These require tiny gear teeth, consistent tolerances, smooth rotational motion, durable alloys. To manufacture even a simple gear, you need controlled metal composition, uniform hardness, fine cutting tools, measurement standards, which implies advanced metallurgy, chemical refinement, carbon control, quenching, precision abrasives, stable tooling. Here is the contradiction. Can low-precision tools generate high-precision components? Engineering answer: not efficiently, not repeatably. Precision is not a one-time achievement. It is a system property, and systems do not emerge by accident. Part 3. Screw-cutting lathe paradox. Industrial historians reference Henry Maudslay and the screw-cutting lathe. Standardized threads turn into interchangeable parts, but the lathe requires precision metal components. Those components require earlier precision tools. This creates a tolerance cascade. Each generation depends on the previous one. So the core question: where does the first precise system come from? Mainstream answer: gradual improvement. Critics counterpoint that chain lacks a clearly demonstrated starting node. Part 4. The invisible infrastructure stack. According to economic historian Nathan Rosenberg, every technology rests on hidden layers: mining, fuel, metallurgy, transport, measurement, skilled labor. A steel hammer is not primitive. It implies an entire industrial base. This is where the paradox stops being ancient history and becomes a modern problem. Let's scale upward. Ball bearings, jet turbines, microchips. These are not inventions. They are ecosystems. A microchip requires rare earth extraction, ultra-pure chemicals, photolithography optics, clean rooms, global logistics. Remove enough layers, the system collapses. And to push this further, some fringe engineering communities argue that even today, certain components like high-precision bearing balls and advanced microchips cannot be manufactured using the technologies we officially claim to possess. Part 5. The irreversibility threshold. Key insight: technology is not fragile because it's advanced. It's fragile because it's interdependent. You can rebuild a stone tool easily. You cannot rebuild semiconductor infrastructure from scratch in a collapsed system. This is the irreversibility threshold. Beyond a certain complexity, collapse skips levels. Not gradual regression, but structural drop. Part 6. Collapse and rebuild dynamics. Now the symmetry appears. If complexity is hard to build upward and hard to rebuild downward, then technological history may not behave like a clean upward slope. It may behave like phase shifts. Alternative researchers extrapolate. If prior civilizations crossed similar thresholds, their collapses could erase upper layers almost completely. Archaeological findings demonstrate that metal artifacts are the rarest of all material types. Metal is highly susceptible to corrosion, and therefore it is often the first evidence to perish in the historical limbo. What survives though? Stone, durable architecture, fragments, not chips, not turbines, which raises a legitimate concern. The absence of advanced tools and equipment in the archaeological record would not necessarily prove that those were absent in ancient times. Important clarification. There is no verified evidence of global advanced pre-modern industrial civilizations. But the system's logic makes reset cycle theories intellectually tempting, because we can now see how fragile complexity actually is. Part 7. The loop closes. The first tool paradox questions. How does complexity begin? The irreversibility threshold questions. How does complexity disappear? These are mirror problems. Creation and collapse. We study how civilization rises. We rarely analyze how it structurally fails. So this is no longer just a question about the past. It's a question about how much of our own world is actually rebuildable in case of an extraordinary collapse event or process. Technological history may not be linear. It may not even be cyclical. It may be layered accumulation with hidden fragility. The first tool paradox shows how hard it is to rise. The irreversibility threshold shows how fast it is to fall. Between them lies the real structure of civilization.